Understand why we can trust random samples and randomized comparative experiments, we need to look closely at chance behavior. The big fact that emerges is this: chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. The idea of short-term unpredictability. Suppose we want to know what proportion of all adults bought a lottery ticket in the past 12 months. So we take a sample of 1,027 adults and we found that 472 bought lottery tickets. So the sample proportion is about 0.46. So how good is that at estimating the proportion of all adults who bought a lottery ticket in the past 12 months? Well, if we were to take a different sample of 1,027 adults, we might get a completely different sample proportion, like 0.66. That's considerably different. So which one's correct? Well, we don't know at the moment. We can't trust the result of a single sample, but we can use the laws of probability to give us an idea of the variability among the different samples. And that's why we study probability. So we'll look into some of the basic concepts of probability. The general idea of it, talk about probability models, some of the rules of probability, the difference between finite and discrete probability models, and we'll talk about continuous probability models. Those actually are very important in what we're going to do in a little bit. Okay, so the idea: chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. We call a phenomenon random if individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. The probability of any outcome of a chance process is the proportion of times the outcome would occur in a very long series of repetitions. Tossing coins is a fairly common way to explain, to talk about and illustrate probabilities. On the left, there's the proportion of heads against the number of tosses. So the first toss we got heads, probability of getting heads is 100%. And for the second toss it's 0, so it goes down to 0.5 and so on, and it fluctuates all around. Notice there is that sort of short-term fluctuation. We can't predict how many heads there will be in a small number of tosses. But as the graph on the right shows, in the long run, the cumulative probability, the number of heads that show up in, at least in this case, 500 trials, is beginning to approach half. There are several myths of chance behavior that we need to address. First, the idea of probability is that randomness is predictable in the long run. Our intuition tries to tell us that random phenomena should be also predictable in the short run. However, probability does not allow us to make short-run predictions. We can't predict what the next toss of the coin will be, whether it's heads or tails, but we can tell in the long run about how many heads there will be. The myth of the law of averages. Probability tells us random behavior evens out in the long run. Future outcomes are not affected by past behavior. That is, past outcomes do not influence the likelihood of individual outcomes occurring in the future. So just because we got 4 heads in a row doesn't mean we're more likely to get tails on the next one. Okay, probability models. The descriptions of chance behavior contain 2 parts: a list of possible outcomes and a probability for each outcome. The sample space of a chance process is the set of all possible outcomes. So in tossing a coin, the possible outcomes are heads or tails. In tossing 2 coins, the possible outcomes would be heads on the first one, heads on the second, heads on the first, tails on the second, tails on the first, heads on the second, or tails on both. An event is an outcome or set of outcomes of a random phenomenon. That is, it's basically a subset of the sample space. A probability model is a description of some chance process that consists of two parts, a sample space and a probability for each outcome. For example, let's give a probability model for the chance process of rolling two fair six-sided dice, one that's red and one that's green. Well, the outcomes look like this. In this case, there are actually 36 different outcomes. We can get a 1 on the red die and a 1 on the blue, or green, I guess it is, or any combination of all of those. No, we're making the distinction between red 2 on the first one and 1 on the second, and 1 on the first one and 2 on the second. Those are different outcomes. In this case, since the dice are fair, each outcome is equally likely. So each one of these outcomes has a probability of 1 out of 36. So let's roll two dice. The sum of the dice is 5 is an event. And in this case, it consists of the following outcomes: 1 and 4, 2 and 3, 3 and 2, 4 and 1. Those are the outcomes that satisfy the event. The sum of the dice is 5. All of these outcomes are equally likely, so each outcome has probability 1 out of 36. Since there are 4 equally likely outcomes in the event, the probability that the sum of the dice is 5 is 4/36. Now let's consider the sample space for the sum of the dots on a pair of dice. Not just what the dots are, but the sum of the dots. That's what we usually are interested in when we play a game or something. Well, the sample space consists of 2, 3, 4, 5, 6, up through 12. Those are all of the possible sums you can get when you toss two dice. But in this case, the probabilities are not equally likely. But since we have information about the probabilities for the 36 outcomes for tossing dice, and those are all equal, we can use these to determine the probabilities for this sample space. There's only one way to obtain a sum of 2. Both have to show 1. There are 2 ways to obtain a sum of 3, 1 and 2 or 2 and 1. There are 3 ways to obtain a sum of 4, 1 followed by 3, 2 followed by 2, 3 followed by 1, and so on. So we can construct a probability model for this these outcomes. We know we can establish the probabilities for each and provide a model. So once again, the possible outcomes, 2, 3, 4, 5, 6, all the way up to 12, and then with each of those is a probability based on the 36 outcomes we had before. So for example, to roll a 7, well, if we went back to the table, we'd find that there are 6 different ways that we can get a sum of 7, and so on. Some of the probability rules. A probability is a number between 0 and 1. All possible outcomes together must add up to give a probability of 1. If two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. The probability that an event doesn't occur is 1 minus the probability that it does. For example, if there's a 40% chance it's going to rain tomorrow, it means there's a 60% chance that it's not going to rain. We can turn these into the rules for probability. So the probability, P of A, of any event A satisfies this condition. The probability of the event is between 0 and 1 inclusive. So it can be 0, it can be 1. 0 indicates it's absolutely not possible at all for it to occur. Probability of 1 means there's no chance it's not going to occur. The second rule: if S is the sample space in a probability model, then the probability of the sample space is 1. If we have disjoint events that don't overlap, then the probability of A or B occurring equals the probability of A plus the probability of B. For example, if A and B are the events drawing cards from a deck of 52 cards, the probability of a queen or a king is the probability of getting a queen plus the probability of getting a king. This is called the addition rule for disjoint events. The last rule: for any event A, the probability that A doesn't occur is 1 minus the probability that it does. So, here's an example. Distance learning courses are rapidly gaining popularity among college students. Suppose we randomly select an undergraduate student who is taking a distance learning course for credit, and we'll record the student's age. Here is the probability model. So we have basically 4 categories and the probabilities associated with each of those. First, let's show that this is a legitimate probability model. Well, it needs to satisfy those rules. So in the first case, each probability is between 0 and 1, and the sum of all the probabilities equals exactly 1. So yes, it is a legitimate probability model. Now let's find the probability that a chosen student is not in the traditional college age group. We'll assume that means 18 to 23 years old. So the probability that it's not 18 to 23 equals 1 minus the probability that it is 18 to 23 years. So 1 minus 0.57, and we get 0.43. Notice we could also have gotten the same answer by just simply adding the probabilities that are not 18 to 23. So that means 0.17 plus 0.14 plus 0.12. The first method is just a little bit shorter and works better when there are a lot more categories involved. Okay, so one way to assign probabilities to events is to assign a probability to every outcome, then add these probabilities to find the probability of any event. This idea works well when there are only a finite, fixed, and limited number of outcomes. So a probability model with a finite sample space, that is, there are just a finite number of outcomes, is called finite. To assign probabilities in a finite model, we simply list the probabilities of all the individual outcomes. These probabilities must be numbers between 0 and 1 that add to exactly 1. Then the probability of any particular event is the sum of the probabilities, just like we saw with the sum of the dice. So here's an example. The numbers 1 to 9 occur randomly in some processes like lotteries, but they don't occur random in other processes. There's actually a man named Benford actually described this particular phenomenon for certain processes, and it's called Benford's law. So the first digits of numbers will often follow this particular model, where the probability that the first digit is 1 is about 30%, the first digit is 2 is about 17%, and so on. So, as an example, Minnesota has over 11,000 lakes, more than 10 acres in size. If we count the frequencies of the digits 1 through 9 that occur as the first digit of the size of each lake, we get the distribution shown here. It actually follows Benford's law fairly closely. We might think that the first digit would just simply be equally 1 through 9 just as often as it shows up. But it turns out that's not always the case. This distribution has been found to apply to a wide variety of data sets, including electricity bills, street addresses, stock prices, population numbers, death rates, lengths of river, and so on. It is widely used in forensic accounting to detect fraud. Now we'll consider continuous probability models. Suppose we want to choose a number at random between 0 and 1, and we allow any number between 0 and 1 as the outcome. Well, we can't assign probabilities to each individual value because there are an infinite number of them between 0 and 1. A continuous probability model assigns probabilities as areas under a density curve. The area under the curve and above any range of values is the probability of an outcome in that range. So, for example, if we consider the numbers between 0 and 1, well, it's what's called a uniform distribution because there's no particular preference toward one number or another. They're all equally likely. So the probability of randomly picking a number between 0 and 1 that is exactly equal to 0.53129888, etc., on and on and on, of picking any one particular number is 0. But we can find the probability of getting random numbers between certain values. So the probability of getting a random number that is less than or equal to 0.5 or greater than 0.8. And notice here, we indicate this with the shaded region in this distribution. So the area between 0 and 0.5 is 0.5. Between 0.8 and 1 is 0.2. So the probability that the random variable takes on the numbers less than 0.5 or greater than 0.8 is the sum of their probabilities using the probability rule. So that's 0.5 plus 0.2, so 0.7. Notice too, the probability that we wouldn't get something in there is if we landed on something between 0.5 and 0.8. That would be 0.3. Normal distributions are continuous probability models. The normal curve itself is a density curve. It is important because there are many phenomena that closely follow the normal distribution. And here are a few examples. As you can see, there are histograms whose models can be smoothed out with a density curve. Example of a normal probability model. The heights of women closely follow a normal distribution with a mean of 64.3 inches and standard deviation of 2.7. If a woman is randomly chosen, what is the probability that she is between 68 and 70 inches tall? So first we need to find the z-scores for each of the values, 68 and 70. The z-score for 68 is 1.37. The z-score for 70 is 2.11. So the probability that a height falls between 68 and 70 inches is the same as the probability of finding a z-score between 1.37 and 2.11. The area associated with z of 1.37 is 0.9147. The area associated with a z-score of 2.11 is 0.9826. So we subtract the two. So the probability that a woman randomly chosen is between 68 and 70 inches tall is about 7%. Now we'll talk a little bit about what are called random variables. So a probability model describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. A numerical variable that describes the outcomes of a chance process is called a random variable. And the probability for a random variable, probability model for a random variable, is its probability distribution. So a random variable takes numerical values that describe the outcomes of some chance process. The probability distribution of a random variable gives its possible values and their probabilities. Keep in mind the probability distribution can be discrete or continuous. So, consider tossing a fair coin 3 times, and we'll define the random variable x to be the number of heads obtained. Well, the random variable x can take on the values 0, 1, 2, or 3 as to how many heads are showing up. Notice, for example, in order for there to be 1 head showing, there are actually 3 different outcomes possible. So, we get this distribution of the random variable. Probability, the value, it can be 0, 1, 2, or 3, and the associated probabilities below. And a histogram of that probability distribution looks like that. There are 2 main types of random variables, discrete and continuous. If we can find a way to list all possible outcomes for a random variable and assign probabilities to each one, we have a discrete random variable. So a discrete random variable x takes a fixed set of possible values with gaps between. The probability distribution of a discrete random variable x lists the values and their probabilities. So the values x1, x2, x3, and so on. Probability p1, p2, p3, and so on. The probabilities p must satisfy 2 requirements. Every probability is a number between 0 and 1, and the sum of all the probabilities is 1. To find the probability of any event, we add the probabilities p of the particular values x that make up the event. I should note here that the values x, there can be an infinite number of these, but there is a gap between them. Discrete random variables commonly arise from situations that involve counting something. Number of dice, number of children, number of cars, etc. Situations that involve measuring something often result in a continuous random variable. For example, measuring heights, measuring temperatures, and so on. A continuous random variable y takes on all values in an interval of numbers. The probability distribution of y is described by a density curve. The probability of any event is the area under the density curve and above the values of y that make up the event. The probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of the random variable. A continuous random variable has infinitely many possible values. All continuous probability models assign a probability of 0 to every individual outcome. Only intervals have positive probability. We saw rolling 2 dice. The sum of 2 dice is a discrete random variable because it takes on only a finite number of values, 2 through 12, and there are gaps between each of the values. For example, the sum of 2 dice is 5. The probability that the sum of the 2 dice is 5 is about 0.11. The heights of 18-year-old men, by contrast, is a continuous random variable because it takes on an infinite number of values. The variable height takes on every real number between 59 and 77. And actually it continues on forever to the left of 59 and to the right of 77, at least in theory. Now, the probability that the variable takes on any single value is 0. We can only determine probabilities between values. And the probability that the variable falls between any 2 values is the area under the density curve. So, to review, we described the idea of probability. We described chance behavior with a probability model. We applied some of the basic rules of probability, described finite and discrete probability models, described continuous probability models, and we defined random variables.